Hello, everybody, and welcome to Practice Exam 2, an organic chemistry experience. So this first question is all about acid-base strength trends. So here we see that we're trying to compare the strength of 4 different carboxylic acids. Now, by virtue of being carboxylic acids, the acidic proton is always that OH bond that we're trying to break. So if you just have a run-of-the-mill carboxylic acid, how can we influence it to make it stronger? Enter the inductive effect. The idea behind the inductive effect is that by adding electronegative atoms in the neighborhood of the carboxylic acid, so for example, if I add chlorine, those are pretty electronegative right here, what that will do is actually have an effect that further polarizes this OH bond. And remember, the more polarized the bond is, the stronger the acid will be, because more polarized bonds are weaker and easier to break, so it'll be easier for it to give up its hydrogen. So the question becomes, how can we really trick out our carboxylic acid? Well, what if instead of chlorine, we added something more electronegative? Like, what if we added instead, wait for it, something like fluorine? Whoa, that would have an even more pronounced effect. But how can we make these have even more of an impact on the carboxylic acid itself? By getting it closer, because the closer it is to the carboxylic acid, the more pronounced effect it's going to have on this OH bond. So in this particular problem, we have these carboxylic acids that all have 4 carbons on them, and most of them, well, 3 of them, have a fluorine. So the one that's going to be the weakest is 3, because you'll notice that 3 doesn't really have any electronegative atoms to help further polarize the bond through the inductive effect. The other 3 answers all have a fluorine and just 1 fluorine, so it's not the number of fluorines that makes a difference here. So how can we rank these? Well, the one that has the fluorine that's closest to the OH bond, so the one right here, is going to be the strongest. It'll have the most pronounced impact. Then 2, and then 4, because 4, notice the fluorine is furthest away from the carboxylic acid. Part B follows a similar idea. It's also about the inductive effect, but here we're trying to rank them from least basic to most basic. So this relies on an important concept, that is, the weaker an acid is, that equates to a stronger conjugate base. So weaker acids equal stronger conjugate bases, and vice versa. Stronger acids mean weaker conjugate bases. So for a problem like this, we can almost visualize each of these as if they're acids, instead the conjugate acids, and basically rank them in reverse order. So if we consider these, which of these would be the weakest acid? Well, it'd be the one with just these 3 hydrogens on it. So that's just acetic acid. It's a pretty weak acid. It's an okay acid, but they're certainly much, much stronger. So this is the weakest acid, which means it has the strongest conjugate base. So we're going to rank that there. On the flip side, which of these would be the strongest acid? Well, that would be the one that has these 2 chlorines, because 2 chlorines is more electronegative than 1 chlorine collectively, which is more electronegative than 1 bromine. So the weakest of these bases would be a 3. So I'm going to get rid of these protons now, just so we can take an actual look at the bases themselves. Ta-da! And again, this just comes down to this idea that weaker acids have stronger conjugate bases and stronger acids have weaker conjugate bases. So since we're doing a reverse ranking order here, the next one is going to be 1, the one that only has 1 chlorine, because this would have a this would be a weaker base than 4, because 4 has the 1 bromine here. Bromine is less electronegative than chlorine. So again, if we think about the conjugates, the conjugate acid of the one with the chlorine would be stronger, which makes the base here weaker than the one with the bromine. And here's our order. Again, basically just reversing the order of acid strength. In this problem, we're looking at a different trend. So actually, we're looking at two different trends, it turns out. We're trying to find out which are going to be the most and least acidic here. So the most acidic one is going to be this fellow right here. The idea is if you compare a silicon-hydrogen bond versus a carbon-hydrogen bond, a silicon-hydrogen bond is significantly longer than a carbon-hydrogen bond. Longer bonds are easier to break and therefore give us stronger acids. And now note, this is only when we're looking at a hydrogen directly bound to a certain atom. So size is going to be very important because longer bonds are a lot easier to break. So anytime you're trying to compare the acid strength of an acid where the hydrogen is bound to a different atom, we're just going to call it generically X. If you're comparing different atoms that are in the same column on the periodic table, the further down that atom is, the stronger the acid is going to be, because the further down on the periodic table we go, the larger the atom becomes. So silicon, again, is a lot larger than its neighbor carbon, so this bond's a lot easier to break, which makes this a stronger acid. So that's part one of what makes this the strongest acid here. The other important thing to note is to think about how the conjugate base is stabilized through resonance. If we deprotonate this molecule, we get this conjugate base. A negative formal charge on an atom is a burden for it to carry. So it helps if there are resonance structures available, ways that the electron density can be moved throughout the molecule in order to stabilize the conjugate base. So for example, here, we could throw these electrons right here, and then push these electrons right here. This actually has a number of resonance structures. I'm not going to draw them all here, but basically any time that you see a lone pair of electrons adjacent to a pi bond, usually a double bond, that means that you have resonance opportunities available. That stabilizes the conjugate base. And what that means is if an acid is able to lose a proton and turn into a more stable species, now granted, this is less stable than what we started with, but by having resonance, it makes it more stable than it would be without that. So by making a product more stable, it lowers its energy and makes it more favorable. So that makes the whole acid-base reaction more favorable. So that gives us a stronger acid. So if the base is stabilized through, if the conjugate base is stabilized through resonance, that gives us a stronger acid. Long story long, this is the strongest acid. So the weakest acid is going to be its neighbor. This one right here. It's got that short carbon-hydrogen bond, very difficult to break a carbon-hydrogen bond, and there is no resonance stability conferred in the conjugate base. Speaking of breaking carbon-hydrogen bonds, it's generally very difficult to do so, but there are ways of making it easier. Enter the trend in D. So all three of these have carbon-hydrogen bonds. So which one is going to be the most acidic? This comes down to the hybridization. If we look at the hybridization on these atoms, this is sp3, this is sp2, and this one here is just regular old sp. It turns out there's actually an electronegativity difference in different hybridizations of the same element. And the most electronegative of these would be sp. Most electronegative. After that, we have sp2, and the least electronegative is going to be sp3. So if we're looking at hydrogen bound to atoms of relatively same size, so like if we're looking at the same period of the periodic table, or in this case, we're looking at the same atom, the more electronegative the atom is, the more it'll pull electron density away from the hydrogen, and the easier it will be to pry away that hydrogen. So the most acidic of these is going to be the one with the sp hybridized carbon. The least acidic, on the flip side, literally, is going to be this one, the sp3 hybridized. In problem 2, we're trying to find the pKa of the conjugate acid of both of these chemical species. So let's consider the first one, acetic acid. If we look at the conjugate acid of acetic acid, it turns out we can consult our pKa table to figure this out, but the oxygen that accepts the proton is actually this oxygen here. This is a common misconception about, generally carboxylic acids act as, acids. But if you have a strong enough acid that you're pairing them with, then you can protonate them. But it's specifically that oxygen that gets protonated. It is not this one right here. And we can see that if we look at our pKa table. So, also consulting the pKa table, we can see that the pKa of this conjugate acid is negative 6.1. So let's do the same thing for this molecule down here, aniline. The conjugate acid of aniline looks strikingly similar, as do all conjugate acid base pairs, except we add a proton to where that lone pair of electrons was. And this one has a pKa of 4.6. In this next problem, we're trying to deprotonate this particular molecule, I believe naphthalene. So we have our acidic proton noted, and consulting our pKa table, we can see that the pKa of this particular proton is equal to, actually a surprisingly low number, because it's usually hard to pry a hydrogen off of a neutral nitrogen. But this is a pKa of 8.3, and it's actually because the conjugate base is resonance stabilized, as we actually looked at in our homework assignment. Okay, so how can we figure out if a base is going to be strong enough to meaningfully deprotonate this? This all comes down to our analysis of acid-base equilibria. If we want a base to be strong enough to deprotonate an acid, so if we want a reaction that heavily favors the products more so than the reactants, as indicated by that larger arrow up there, how can we figure out if this is going to proceed forward? Remember, it all comes down to the pKa of the acid and the conjugate acid. So let's say that the acid that we're trying to deprotonate has a pKa equal to some arbitrary variable x. In order for the reaction to favor the products here, we would need the pKa of the conjugate acid to be greater than x, because the equilibrium favors the side with the greater pKa. Now, remember, quick disclaimer here, that if they're within 2 pKa units of one another, then it's more of a true equilibrium, and neither side is really heavily favored. So as long as this side here, this is a pKa that's greater than 2 over the pKa of the acid, that means we're looking at a favorable reaction. Long story long, all we have to do is look at the conjugate acids of these molecules and compare their pKa values to the thing that we're trying to deprotonate. So, for example, for this first one, the conjugate acid looks like this, and this has a pKa equal to 17. Now we compare that to this 8.3. Is it greater than 8.3? Well, yes. Yes, it is. So, this base will be strong enough to deprotonate that acid. If we go through and look at the other ones, so the pKa of this conjugate acid is equal to 4.8. Not greater than 8.3, not going to get the job done. If we look at Cl minus, forget about it. HCl has a pKa of, I believe, -7. It's either -6 or -7. Pretty sure it's -7. Anyway, regardless, it's far more negative than the pKa of our acid that we're trying to deprotonate. So then it leaves us with our last molecule. Its conjugate acid is this molecule, ethine. And ethine has a pKa of, drumroll, 25. Far greater than the 8.3 to allow this to happen. So, long story long, we just need to make sure that whatever base we're trying to deprotonate our acid with, we need to make sure that the conjugate acid has a pKa that is greater than, and specifically 2 greater than, although we won't give you one that is within 2 and be like, ha ha ha, gotcha, this one's within 2. We'll pick ones that are pretty noticeably different here. But just make sure that the base that you're looking at has a conjugate acid with a greater pKa value than the acid that you're trying to deprotonate, and that will get the job done. All right, now we've got some true and false questions and some which of these can be nucleophiles and which ones can and which ones can be electrophiles, et cetera, et cetera, et cetera. So, which of these cannot act as a nucleophile? So for something to act as a nucleophile, it needs to have either a lone pair of electrons available, so lone pairs can work well for that purpose. It needs to have a pi bond, if it doesn't have a lone pair of electrons, because pi bonds have a lot of electron density. In some rare cases, we have sigma bonds that can act as nucleophiles, but we'll encounter one example way later in the course. So if we consider these, all of these have either pi bonds. So for example, right here, there's a pi bond, or lone pairs of electrons. So if I were to draw in the lone pairs, these all have negative charge density on them. They can donate. The only one that doesn't is this ammonium cation. And generally speaking, this isn't always the case, but the more positively charged something is, the less good it's going to be at being a nucleophile, because for something to be a nucleophile, we need negative charge density to donate itself. So this is going to be our answer here. Now the next one says which one cannot be an electrophile. So if we look at electrophiles, they need to have a partial positive charge on them or a full-on positive charge that can accept electron density. The only one that doesn't have that here is cyanide, Cn minus. So Cn minus looks like this. We have, we have our carbon with a negative formal charge on it. We have our nitrogen, which has a negative partial charge on it. This is just electron city. It's so much negative charge density. Forget about it. This is not going to want to accept electrons. So this is going to be our answer here. So generally speaking, things are more nucleophilic, and this is a generalization, but the more negatively charged something is, the more it tends to act as a nucleophile. The more positively charged something is, the more it tends to act as an electrophile. There are exceptions to this, but that's a good way that you can kind of think about it if you're trying to start to narrow down your choices. Now let's look at these 3 true-false questions. First one, reactions run under basic conditions can have neutral, negatively, or positively charged intermediates and products. This is, well, false. The thing that makes this false is this positively, no, not the case. If something is in a basic environment, that means there's an abundance of negative charges. Those negative charges are going to be pulling off protons. It's going to make it impossible to have a cationic intermediate. So neutral, check. Negative, check. Positive, not so check. The next one, intermediates do not have real bonds and are represented by the highest energy point on a reaction coordinate diagram. So this one is, wait for it, also false. Intermediates do have real bonds. This is actually describing transition states. Transition states are not isolatable molecules. They only exist for a split second before they either move forward or move backwards and become an intermediate or a reactant or a product. So transition states or activated complexes are what this is actually describing. And then finally, true or false? Trends in nucleophilicity are always the same as trends in acidity. Oh, that always word. Well, this one is, wait for it, I'm just kidding. This one's also false. All 3 of these are false. They're not always the same. They're often related, but this is actually a case of kinetics versus thermodynamics. So acidity and basicity versus electrophilicity and nucleophilicity, they actually have to do with different properties. One of them deals with how fast a reaction goes. The other one deals with how stable the reaction is, or how its relative changes in energy. Speaking of reaction coordinate diagrams, let's consider this one for the next 6 questions. So the first question says, label the transition states. So the transition states, I'm just going to call them TS's. These are the apexes, the relative maxima on our graph. The next one says label the intermediates. So I'm just going to appropriately call these int. So the intermediates can be found at these energy wells here. So at the beginning we have our starting material reactants, at the end we have our products. Any valley in between is going to be an intermediate. Next it says label the energies of activation. So there are actually 3 steps here. This is the first one. Each step has its own activation energy, its own energy barrier. You can really think of chemical reactions as being hills that you can think of it as kind of like rolling a ball up a hill. It always takes energy to roll a ball up a hill. Likewise, it always takes energy to get to these energy maxima. And as we'll see in a moment, the larger that hill is, the longer it's going to take and the more energy you're going to need to put in. So these are the 3 activation energies of the 3 different steps. So check. How many steps are there? Each hill represents a step. So there are 3 elementary steps here. Which one is the slowest? So the slowest is going to be the one with the greatest activation energy. Again, going back to that analogy about a hill, the larger the hill, the longer it's going to take to roll over it. So this one here is going to be our slowest step. So the 3rd step is going to be the slowest. And then finally, our reactants are products favored. And to answer that, what we can do is consider the relative energy of the reactants and products. So if we were to draw a line across like this and see what is happening with our relative energy levels, notice here that our overall delta E, or delta G, this is free energy, is positive. So that means that the products are higher in energy. They're less stable because the higher the energy, well, that's going to lead to a less stable situation. Lower energy is more chill, more favorable, more stable. So what's going to be favored here? The reactants, by virtue of being lower in energy. This next question asks us about the different roles of the different molecules in this reaction, and then asks us to figure out what each elementary step is. So let's go through and figure out the roles on each of these. Molecule A. So we start with A. A is used up and it's never reformed. So anything that only appears on the left-hand side of a reaction is a reactant. And in fact, let's just take a little note of this. So reactants are used up, never reformed. If they're reformed, they're a catalyst. We'll talk about that in just a moment. So they only appear on the left-hand side. Let's write that too. Only appear on left-hand side of the various elementary steps. Up next, we have molecule B. So B is formed, but it only lasts for an intermediate amount of time because it's made and then, oh, sorry, B. It's been fun knowing you, but you were made and then you were used up. It was only there for an intermediate amount of time, and guess what? It's known as an intermediate, appropriately enough. So an intermediate is something that is made in a step and then used in a subsequent step. It doesn't have to be the next step, but it's made, it exists for a transient amount of time, and then it's used up again. Up next, we have molecule C, well, aka ion C. And I've got my eye on this bromide. Notice that it's made and then used up subsequently. So this is also going to be an intermediate. Okay, up next, molecule D. So D appears right here, and that's the only place where it appears here. D is a product. It is only made throughout the course of the reaction. So our products only appear on the right-hand side of a reaction. They are made throughout the course of it. But what of E? Molecule E, well, it was made in a previous step and then used up. That makes it an intermediate. And then finally, we have molecule F. It only appears on the right-hand side that makes it a product. So the only thing that we don't see here is a catalyst. And so a catalyst is basically like an anti-intermediate. A catalyst is used up and then reformed. And the idea is that once it's reformed, it can help facilitate the reaction over and 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 over again. So it appears on the left-hand side, and then later in a subsequent step will appear on the right-hand side. So it's used but then reformed, and that's what differentiates it from a reactant. And the last part of this question is, what are each of the elementary steps? So in this first one, notice that we have a true acid-base reaction. We have a proton here, and that proton gets transferred over to here. Well, I covered up this becomes 2. So what is this? This is a proton transfer, appropriately enough. So true acid-base reaction happening here. So for the next one, what's happening here? Well, in this reaction, in this, elementary step, we have this bond getting broken here, and we're splitting this up into 2 different molecules. This is an example of heterolysis. Then finally, we have our last elementary step, where the bromide ends up moving into this cationic spot. This is called a coordination. So as we'll see later, there are reactions where, say, proton can move, but it's actually, for example, an addition reaction or elimination. And so a proton transfer reaction is a true acid base. We have our base, we have our acid, and we have a proton move between it. We'll see that addition and elimination reactions both involve pi bonds. More on that in a little bit. We'll cover those. But just note that some of these can look like other types of elementary steps, so just make sure you're familiar with what distinguishes it as one of the true 7 types of elementary step. All right, in this problem, we're trying to figure out which of these is not an appropriate resonance contributor or is not an appropriate conjugate base or resonance contributor of aforementioned conjugate base. So what we'll do to start this is imagine what the conjugate base looks like. So it looks very similar. In fact, the whole molecule is the same, except for one key difference. We've taken our acidic proton and we've removed it. So I'm just going to put the lone pair here and our negative sign here. So this is our conjugate base. So right off the bat, we can eliminate this as an answer choice. I'm actually going to put checks next to it because I'm just going to show which ones are actually the conjugate base and contributors. So this one's fine. Now then, what do the various resonance contributors look like? So for the first one, what we're going to do is we're going to take these electrons here and we're going to push them this direction. Anytime you have a lone pair of electrons adjacent to a double bond, you can do some electron pushing like this. And we're going to push these electrons back to make our first resonance contributor. So the first resonance contributor is going to look like this. Nothing happened over here. But what we did do is create a double bond, and I'm not drawing in the hydrogen. Well, I'll draw it in really quickly. It's right there, but we don't need it because it's a skeletal structure. We have our oxygen, and our lone pair of electrons jumped up here to move that formal charge. Okay. So this is resonance contributor number 1, which means this one is also good. Now, the other way that we could push our electrons is we could instead plop these electrons right here and push these electrons back, which would give us this structure with a lone pair of electrons here and the negative formal charge moved. So this one here is also good. The only one that does not work is this one right here. And what this actually does, one of the rules of resonance is you can't move around atoms. And if we think about what's happening with our base here, so there are 3 hydrogens here, right? And notice that this particular structure here, there can only be 2 hydrogens. Let me change the color on that just so we can see it. Because we can't have a hydrogen, or a carbon, excuse me, with 5 bonds. So anytime you move around atoms, that is not a resonance structure. Or in this case, we actually changed the number of atoms. So no, this one's not going to work. Nay. This question asks what type of elementary step is being depicted by each of the following electron pushing arrows. So for posterity's sake, I'm also going to draw the products of these. In this first one, notice that we're using a pi bond here to act as a nucleophile. And in the process, we're destroying that pi bond. So what this is actually going to look like is we're getting rid of the pi bond, and we're throwing a lone pair of electrons onto the sulfuric acid. And we'll draw the rest of this. Okay, cool. Now then, the hydrogen here was lassoed and moved. And it doesn't matter what carbon we put it on in this molecule. We'll learn later that it actually does matter if you have an asymmetrical molecule, or if you have a different number of carbons, like a secondary carbon or a tertiary carbon. We'll talk about that later. I'm just going to put it arbitrarily on this carbon here. And the other carbon is going to get a positive formal charge. So anytime a pi bond attacks one carbon, well, as long as it attacks a hydrogen, one carbon will get a hydrogen, the other one will get a positive formal charge. And again, we could have reversed this. Either one would be correct. So this is an example of an addition reaction. And the way you can always tell an addition is the key lies within the pi bond. If you destroy a pi bond, that is an addition. On the flip side, if you make a pi bond, that is an elimination. And we'll see that actually in just a little bit. Spoiler alert, C. So for the next one, let's figure out what the next one makes. So the product here is going to look like this. We're forming a bond. So this is a bond formed. And we're forming it right here with this particular carbon. So I'm going to draw this in, attached to the oxygen. And there's a hydrogen. And this actually has a positive formal charge on it. Okay, so here's our product. And I'm going to erase this little thing here just to mitigate any confusion because it kind of looked like a hydrogen there. It's not, though. So this is the product. And here what we have is a lone pair of electrons donating themselves into an area that's electron deficient. So in this case, a carbocation. So anytime we have a lone pair donating itself into a specific atomic site, what we're looking at is a coordination. So it's donating the lone pair of electrons so that it can help eliminate that positively charged carbon there. Okay, and for this last one, what our products are going to look like, or we actually formed a pi bond right here, and that came because of these electrons. And we formed hydronium, cool. Just looks like this. Okay, and anytime we form a pi bond, we're looking at an elimination. All right, in this problem, we're trying to figure out so here we have this polypeptide here, and we want to know the overall charge at 2 different pHs. So this falls down to one rule, and that's if pH is greater than the pKa, that means that a particular functional group is going to exist in its deprotonated form. If, on the other hand, the pH is less than the pKa, we have a really acidic environment, then this is going to exist in its protonated form. After that, we just need to look at each functional group individually and figure out if it has a charge or not. So let's go through and do this at a pH of 1. So looking at each of these numbers, so pKa equals 3.9. Will it be protonated or deprotonated? It is going to be protonated. So this proton, this hydrogen will be on there. Same thing for this one, because this is 2.1. Notice that the next one says the pKa of the conjugate acid is 12.5. So how does 1 compare to 12.5? Well, 1 is less than 12.5, which means this will be protonated. So I'm going to draw in and make this its conjugate acid. So what I'm going to do is I'm just going to draw the hydrogen here, and we now have a formal charge of +1 on that nitrogen. Okay, up next, this hydrogen is protonated. And finally, so it seems like all of these are actually protonated, nothing too exciting going on here. This last one is also protonated. And anytime an amine is protonated, it has a positive formal charge. So checking all these charges, all the carboxylic acids are neutral, and all of the amines have a +1 charge. So this is an overall charge of +2. Cool. Now let's do the same thing at a much more basic pH. So I'm just going to clear off this board here. And the way that we're going to do this is I'm going to go through, and if something is deprotonated, I'm going to cross out the proton if it's already drawn in. So starting with this first carboxylic acid. At a pH of 11, well, notice here that the pH is greater than the pKa, which means this will be deprotonated. So what we're going to do is we're going to scratch off this hydrogen because it's gone. And anytime you have an oxygen that has one bond and it would have 3 lone pairs here, this will have a negative formal charge. Same thing for this one here. And same thing for this one here. Now then, looking at the amines. In terms of this one right here, oops, we have some stray marks going on. So we have a pK of the conjugate acid is 9.7. So at 11, the pH is greater than the pKa, which means this will be deprotonated. So it would exist with that lone pair there. However, this one has a much higher pKa, 12.5. This one will be protonated. So I'm going to draw the hydrogen in like so. And our total charge is we've got 3 negative charges, a 1, a 2, a 3, and then we've got this 1 positive charge. So -3 plus 1 is -2. Oh. Up next, we're trying to figure out what's going to be the acid and the base. We're going to predict the products, and we're going to draw the electron pushing. So what we're going to do first is look up the pKa values, if we can find them for each of the molecules. Both of these are on our table. This one has a pKa of 20, and phenol has a pKa of 10. If you're looking between 2 reactants and you're trying to figure out which one is going to be the acid, the one with the lower pKa is going to be the stronger acid, which means it's going to act as the acid. Now, another thing to note here is sometimes you won't find something on a pKa table, on our pKa table for this type of problem. If so, you can assume that it cannot act as an acid. So this is going to be our acid. This is going to be our base. And the way all acid-base reactions are going to work is we're going to use our lone pair of electrons on our base, and it's going to grab a proton from our acid. Always make sure that you're starting at a lone pair of electrons for an acid-base reaction, and always ending on a hydrogen for an acid-base reaction. Then we're also going to push these electrons from the hydrogen, well, at least that we're connecting the hydrogen to the oxygen, over to the oxygen. So what are our conjugates going to look like? They're going to look like this. We're going to have, I'm going to draw in the scaffolding first here. So they're going to look strikingly similar to the molecules that they came from. The only difference is we're going to have a hydrogen now on our conjugate acid. This is our conjugate acid, and we're going to put a lone pair here on our conjugate base. In terms of the pKa, we don't care about the conjugate base. We can just put an X there. All right. Oops, sorry, flip those around. Okay, now then, we need to find the pKa of our conjugate acid. And if we look at our pKa table, this has a pKa of negative 7.3. Cool, we're almost done. Now all we have to do is compare the pKa's of our acid and our conjugate acid. The equilibrium is going to favor the side with the greater number, unless they're within 2. If they're within 2, it's going to be more of a true equilibrium. So in this case, 10 is far greater than negative 7.3. So this is going to favor the reactants. Now then, let's do the same thing on the next problem. So for the next one, this first molecule has a pKa of 36. The next one has 10.2. Okay, so this is going to be our acid by virtue of having the lower pKa. This is going to be our base. And our base is going to reach out and grab a proton. These electrons are going to jump onto this oxygen here. And we're going to form our conjugates. So our conjugates, again, look strikingly similar. We have our nitrogen. We have a hydrogen. I'll finish drawing that in a moment. And then on the other side, we have our carbonate. And the only differences, again, are that we had a proton being transferred between the two of these. So if we look at these, this is our conjugate base, this is our conjugate acid. And dagnabbit, I did it again. There we go. Okay, now then, our conjugate acid has a pKa of 11.3, and our conjugate base, we don't care. Now comparing these two values, 10.2 to 11.3, notice that these are within 2. Since they're within 2, this is going to be more of a true equilibrium, and we're going to circle this one right here. All right. Now then, let's do some more electron pushing. In this problem, first we have to identify which is the nucleophile and which is the electrophile. The electrons will always start on the nucleophile, or the arrows always start. So notice that we're starting at this carbon, and then we're pushing our way over here, and then over to here. So the cyanide, the Cn minus, is going to be the nucleophile. And this molecule is going to be the electrophile. And we don't have to write this out, but if we want to, this is the bond forming. And this is a bond breaking. So our products are going to look like this. We have our ring here. We formed a bond on that carbon with another carbon. So this is our first product. And then we also have our bromide, which was kicked off. It acts as what we call a leaving group. Okay. And then what type of reaction is this? This is called a substitution. Because literally, the cyanide substituted itself in for the bromide, the leaving group. On this next one, so this is going to be our nucleophile. It's where the electron pushing arrows start. This is going to be our electrophile, and our products are going to look a little something like this. We have our sulfurous acid formed here. So, oops, should be a sulfur. Okay. So we have that, and then we have our other molecule where we actually formed a pi bond, because notice that this sigma bond here is plopping itself into an already present bond, so that's making a double bond. And then we're also forming water. Water's being eliminated in this reaction. So these are our products, and this is an example of an elimination reaction. And the reason why it's an elimination is, notice that we're forming a pi bond. We're forming a double bond here. So anytime you form a double bond, you're going to want to think elimination. And we're so close. Now we just need to draw some electron pushing arrows, identify the nucleophile and electrophile, and figure out what type of elementary step each of these is. So something we can do is see what changes between these two molecules. Notice that this and this, these are all the same. Nothing's changed here. So our arrows aren't going to really involve that. But what is different is, notice that on this particular carbon here, now it has 4 bonds. And what's it bonded to? Well, it's bonded to this nitrogen. So what we're going to do is draw our electron pushing arrows. We're going to start here at our lone pair of electrons and push right in here. These electrons are going to jump back because notice that in our product here, our pi bond is broken and those electrons jumped up onto our oxygen. Okay, so these are the electron pushing arrows. The nucleophiles where the electrons start, the electrophiles are where the arrows go. And then finally, this is an example of an addition reaction. What's basically happening here is this molecule here, aniline, is adding itself in, but the way you can clearly tell that is that we're breaking a pi bond. Breaking a pi bond should be a cue that you're looking at an addition reaction. So this pi bond is broken. That's what tells us we're looking at an addition. For step 2, notice that we're taking this chunk here and we're breaking it off onto its own. Also notice that we're forming a pi bond where there was once no pi bond. So what we're going to do is plop these electrons right here. That's how we get our pi bond. And then we're going to push these electrons over here. That's how we break that other bond. So there we have our electrons. This is an example of an elimination. And the reason why it's an elimination is because we're forming a pi bond. Elimination and addition are, in effect, opposites of each other. The other thing to note here is that because we're only starting with one molecule, there is no true nucleophile nor electrophile. All this is taking place within the same molecule, which is why you don't have to circle nuke or elect. And we have our final step where we have this lone pair of electrons reaching out and yoink, grabbing on to this proton here. These electrons jumping onto the nitrogen to make our products. And this is an example of a true proton transfer. So this is the nucleophile, it's the electrophile, and this is a proton transfer. And our proton that was transferred is just this fellow right here. Notice it's on this molecule and the reactants, and then, whoa, it was transferred. It moved over here in the products. So that concludes it. If you felt comfortable going through this practice exam, if you felt good when you were taking it and you understand all of this, you should do really, really well on the actual exam. And that's exactly what we're confident you'll do and are hopeful you'll do. So keep up the awesome work and rock that exam.